Hi everyone, thanks for checking out this video. So this is going to be a video about the SIR model, which is a model that's used in epidemiology to study like the spread of infectious diseases. And I'm going to be like telling you guys a bit about the model and then showing you how to implement it in Python to do a simulation of it. And so this is going to be a video about like the deterministic version of the model. So we're going to be looking at ODEs and then simulating the ODEs. But if I have time in the future, I may also make like a video on the stochastic version of the model. But yeah, for now, I'll just be like ODs and all deterministic. Um, yeah, okay, so let's talk a bit about the model. So these are the ODEs here. There's three ODEs, and then this fourth equation is just defining this parameter n, which is like the sum of all of the other variables, which we use as like a denominator in some of these fractions. But yeah, so these are the three main equations here. So we have one equation for this variable called s, and s here is the number of people in the population who are susceptible to getting this infection, and then I is the number of people who are currently infected. They're currently infected with the disease, like this virus or whatever that's spreading around. And then R is what's called the removed variable. So they're removed from being infected or susceptible. So these people who have been infected and have either died from the illness or they've recovered and are not susceptible anymore. So an assumption we're making here is that if you get the disease once and you recover, you can't get it again. So then you become part of this R category, which means you're removed from the pool of susceptible people. Okay, so again, so S is susceptible, I is currently infected, and then R is removed. I mean, you can't get it. You can't get it anymore. And then also, like I said, like n is just this variable that's the sum of all the people in all the different stages. Okay, so with S, you might notice with S, it can only decrease. The number of people susceptible can only decrease because we're making an assumption that like the overall population level isn't changing. So there's no one new like entering the population who's susceptible, but it can only decrease, and it decreases when people get infected. So the way people get infected is through contact with someone who's currently infected. So we have this parameter beta, and beta is like the infection parameter that that defines like how people are getting infected, and it depends on the current number of infected people and the current number of susceptible people, because the infections are happening when susceptible people are coming into contact with infected people. So what it depends on both of these variables, and then we have this term beta that just like kind of regulates how the infections are happening based on the levels of infected and susceptible people. And this is all being put over, it's a fraction with the denominator being n, which is the total population level. And you may also see versions of the model that don't divide by n here. That's fine too. I've seen it both ways, but in this model, I'm keeping n in the denominator here because you're going to see in a second that'll allow us to calculate this r naught measure we're going to talk about in a second. But yeah, so we're just putting this whole thing over n, which is the total number of people in the population. And then so our second equation is the ODE for the infected people. So this is increasing with the same term that's like decreasing the level of S is increasing the level of I, because S is decreasing as people get infected, and those people who are getting infected are entering into this I state, this I variable. These are the infected people. So however many people are leaving the S state, those people are all becoming infected and entering the I state. So it just depends on beta and then the level of I and the level of S, and it's all put over n, which is the total number in the population in all the states. And so it's just, yeah, everyone who is leaving the S state is becoming infected and therefore entering the I state. And then the level of I is also decreasing by however many people are either dying from the disease or recovering. And this rate is what we're calling gamma. Gamma is the parameter for this. So this term is just gamma, which is some combination of the death rate and the recovery rate. times I, which is the current number of infected people. So yeah, pretty straightforward there. And then R, which is the removed category. This is just it's going to be positive. It's just the same term. It's the same term that the I state is decreasing by. Those people who are leaving the I state are all becoming this removed state, which means they either died from the disease or are now recovered and not susceptible anymore. So it's just however many people are leaving the I state, that's how many people are entering this R removed state. Okay, so pretty straightforward model. It makes a lot of simplifying assumptions, but that's okay for now for our purposes. If you want to make like a realistic model of like an actual disease, you may need to think about like where these simplifying assumptions don't hold up. For example, like with COVID, for example, like you can even after you've recovered, you can still get it again. So this would be this simplifying assumption in the basic SIR model wouldn't really hold up. There would need to be some term going back from I to susceptible again. Um, Also, if you're lucky enough to have a vaccine for whatever disease you're talking about, you could have some people going directly from susceptible to removed just by getting the vaccines. That would be another case where like the simplifying assumption wouldn't make sense. But yeah, just for like the basic model, the basic SIR model, it's just making these assumptions that you can like if you're in S, you can only go into I, and if you're in I, you can only go into R from there. So that's kind of just how the model goes. If you're susceptible, the only place you can go from there is either just remaining susceptible or becoming infected. And then if you're infected, the only place you can really go from there is you're just going into this removed state. So that's kind of like the simplified model. And then in the news, you guys may have heard people with COVID talking about like the R naught. This R naught measure is basically the beta parameter over the gamma parameter. So that's thinking about how it's thinking about like the parameter defining the infection rate over the parameter defining the recovery rate for infected people. And so this R naught measure is basically a measure of like how many expected new cases you're expected to get for every infected person. So it's basically like if someone is infected, what's the expected number of people they'll spread the disease to? And yeah, there's been in the news a lot with COVID, of course. And a general like rule of thumb is that if the R naught measure is greater than one, then you're going to have like spread of the disease. And if it's less than one, then you're not going to have spread of the disease. So if it's greater than one, that's when you like really need to be kind of getting worried that you could have like an epidemic or even a pandemic on your hands. But if it's less than one, then you should be hopefully okay. At least for the simplified model we're talking about here. Yes, that's kind of the model. So now let's get into writing the simulation in Python. So it's going to be like running a simulation of these ODEs and trying it out to see if we can get some results from it. Okay, so here's our beginning of our Python code. So like usual, just importing numpy snp, importing matplotlib .pyplot as plt, and then importing our scipy ODE solver. So those are the libraries we're going to be using. So if you guys have watched my previous videos, you might hopefully already have a good idea of like how to simulate ODEs in Python. So I'm going to go through this like a little bit fast, kind of assuming that you guys have watched my like previous videos on Python ODE simulations, but I'll try to still like explain what each part is. So the first thing we're going to do is define a variable t, which is going to be the space of time points we're going to be solving over for our results. So we're going to use numpy linspace time point 0 to time point, let's just say 500 for now, and then num equals 1,000, meaning we're getting like 1,000 time points in that space that we're going to be solving over. And then so next we're going to just define our parameters. So we have beta. Let's just call this 0.04 for now, and then gamma. Call this 0.01, and just let's for the purpose of our simulation, let's just make sure that beta is greater than gamma, because that will give us an R naught of greater than 1, which will mean the disease will be spreading. Yeah, okay. And then so next I'll just put these params in a params array just to kind of sorry keep track of them. Okay, so we got our params ready to go in our params array. And then the next thing to do is to define our initial condition. So kind of the convention for this is called the initial condition y0. And this is going to be, we're going to start with 100 susceptible people, 1 infected person, and then 0 removed people. And I encourage you guys to like try out different initial conditions, try some different numbers here. But for now, I'm just going to kind of like keep it simple. Go with 100 susceptible and 1 infected person, and then 0 removed people. Okay, so now we're ready to actually define our simulation. Define our function with our ODEs. So it's going to call this function sim. Although you can call it whatever you want, but I'm just going to call it sim. I'll be passing in our variables array. You guys will see what that is in a second. And then passing in our time points and then our params array. And then, so the first thing we're going to do is define all of our variables. Even though we haven't defined the variables array yet, when this is running through the ODE solver, it's going to be passing something into here with the current levels of all of our variables. So our S variable susceptibles is going to be the first element of our variables array, and then I, the infected people, is going to be second element of the variables array, and then R is going to be the third element. And this is going to make more sense like when if you guys think about like going through the solver is going to be passing in the variables here, and they're going to be getting defined like locally within this function here. But for now, yeah, just trust me, you guys need to like include this part here. Oh, and then also importantly, N is going to be just the current, it's just going to be like the constant population level, which will be all of them combined, all the people in like all different states combined is going to be our N. And then also we want to within our function define the parameters locally. So beta is going to be params, the first element, and then gamma is going to be second element of the params array. So here it might look like just extra work to have to define them like globally out here and then pass them in and then define them again locally. And the reason I'm doing that, like defining like how you can pass them into the function, is just because if you guys want to do a bunch of simulations with like different parameter values that are like predefined, and you want to like vary the parameter values, it'll make sense to be able to like pass them in like this. And it'll like when you guys do stuff like that, it'll make it easier for you guys to be able to like pass them in as an argument into this function here. But for now, yeah, just kind of like trust me on this. And yeah, so the next thing to do is just write out our ODEs like exactly as they are here. We just want to like write them down so that we can return them into the solver. So we're going to say ds dt equals okay. So it's going to be negative beta times I times s, and then all of that over n. So that's going to be our SOD. Okay, sorry. And then dr dt. Di dt. Our infected OD is going to be just the positive of this, right? Yeah, positive that. We talked about like the rationale for doing that before. And then minus gamma times I, right? Yeah, okay. And then so lastly, dr dt is going to be just positive gamma times I. We talked about the rationale for that before. Okay, so now we just need to return all of these. So we're just going to say return, put them all into an array together, and ds dt, di dt, and dr dt, returning all of our equations. Now we're ready to actually put this, send this ODE function into our solver and actually like get some results and solve it. So to actually run the solver, we're going to say y equals, And this is kind of a convention here to call our solver output y. That's why we said our initial condition is y0, and our full output, the full output matrix, is just going to be called y. That's just kind of a convention. I mean, you guys can call it whatever you want, but that's kind of like what people usually call it when you're doing like ODE solvers in Python. That's kind of like the convention. So I'm just calling it that for now, but you guys can call it like whatever. And then call ODE int. This is going to be the actual solver. And then, okay, so just follow me for the syntax for this. Just try to like trust me on what the syntax should be. It's going to be the name of the function is the first argument for the solver. Just the name of the function, and then our initial condition array, y0, our time span that we're going to be solving over, and then, okay, so kind of weird syntax here, but just it's going to be args equals parentheses, params, comma, close parentheses. So just trust me on the syntax for that. I know it's like kind of weird syntax, but just hopefully you guys can take my word for it for now. Okay, so this is going to give us a output matrix, which will have a row for every time point, and then a column for every variable we're solving for. There's going to be the first column is going to be our values for s, second column will be our values for I, and the third column will be our values for R. And then there's going to be a row in that matrix for every time point that we're solving over. Okay, so now let's actually plot this output. Sorry, I'm actually just going to copy and paste some of this just to save time, just because I don't know if you guys want me wasting time like writing all this down. Just kind of being lazy here, copy and paste in some code for the plots, but I'll still tell you guys what each line is. So this is just defining our figure with 3 subplots, because we're going to have 3 different plots, one for each variable. And then this is the code for basically for each subplot, just defining our actual plot. And then for each plot, we're basically saying we're plotting our t, our time span, all of our time points, and then we want to get the values for our variable at each one of these time points. So this one is going to be the s variable. Basically, it's the first column in our y matrix, and then all of the rows for that column. That's going to give us the values of s at each time point, and so we can make that plot like that. And then this will be our I variable. It's going to be the second column in the y matrix, and then all the rows for that column. That'll give us a value of I for every time point we have. And then, so lastly, of course, is R, our removed category. And then we're taking the third column in this y matrix here, and then all the rows in that third column, and then that'll give us a value for R for each of our time points that we solved over. And then down here, just labeling everything. And then for the last one, just labeling the x-axis as time. That'll kind of say that it's time for like all of them. You guys will see. Oh, and then lastly, just plt.show. Okay, so let's run this now, and hopefully it'll work okay. Okay, so, and what did I call this again? Oh yeah. Oh, okay. Wait, whoops. Sorry, it didn't, oh yeah, forgot to make this, forgot to make this a 3. Okay. Sorry, I just noticed that it didn't label the R plot, so I just wanted to change that to make that 3. Sorry about that, guys. Okay, that's better. So we have our plot for S, our plot for I, and our plot for R. And you can see that S is starting at our S initial condition of 100, and then as the disease spreads and kind of like progresses through the population, the number of susceptible people is decreasing because more and more of them are getting infected, and eventually it's eventually making its way to 0, because eventually all of them, the way things are going, like all of them are going to get infected at some point. And then our I variable is the number of current infected people at each time point. So this is increasing at first as more and more of S is getting infected. But remember, when you're in the I category, you can also become removed by either getting better and then you're not susceptible anymore, or like if it goes more tragically, even like dying of the disease. So the infected people, they can either like get better or they can end up dying from the disease. So eventually, the infected people end up also decreasing. And then lastly, everyone eventually in this model for this parameter set, everyone eventually is going to end up in the removed category, meaning you either got the disease and you recovered, or you ended up dying, and then we're still counting you even after you're dead, still counting you in this removed category. And yeah, so I encourage you guys to kind of like play around with different parameter values and stuff, try out different initial conditions and different like values for beta and gamma. Maybe try out one where R naught is less than 1 and see what happens. Yeah, try out different things. I think that's the best way to learn. And as usual, I'll put my code on GitHub if you guys want to download it. And if anyone has any questions, just let me know in the comments and I'll try to answer them. But yeah, so thanks for watching and see you next time.